Good morning, this is Dr. Turner for Integrated Math 3. Today we're going to be looking at 9.3, which is looking at use of the Pythagorean identity. Pythagorean should sound familiar. Usually when we're using that term, we're talking about the Pythagorean theorem. Today we're going to be talking about Pythagorean identity, which is involving values of sine and cosine. Some of those may be coming from the unit circle, but not necessarily. We're also going to be talking about situations where you don't necessarily have to use the Pythagorean identity, but where we're getting it from. So go ahead and get started here. As the name might imply, Pythagorean identity is based on the Pythagorean theorem, where we have in a right triangle a squared plus b squared equal to c squared. Now, we just got done in 9.2 looking at special right triangles on the unit circle, where we looked at values of a given angle, call that theta, and we had a radius of 1. And so what ended up happening is that those points that were on the circle, y ended up being the horizontal distance on the shorter side for our 30, 60, 90, or the longer side for the 60, 30, 90. And then the bottom side ended up being the x-coordinate of whatever that point was on the unit circle. Now, based on that, if I was looking at my basic trigonometric ratios, I end up with x, defining the angles here. Let's say sine of theta, for instance, is equal to opposite over hypotenuse. So y can be defined here as sine theta. And similarly, cosine theta is equal to the adjacent side over the hypotenuse. So x can be defined as cosine theta. Now, based on that, if we use substitution for trigonometric values, x being cosine theta, y being sine theta, and 1 being the hypotenuse, then for any right triangle on the unit circle, we end up with cosine squared theta plus sine squared theta is equal to 1 squared, or just 1. Whereas this first is the Pythagorean theorem. The second here is what's known as your Pythagorean identity. So using the Pythagorean identity, if you know the sine of an angle, you can solve for the cosine of an angle. And vice versa. If you know the cosine of an angle, then you can solve for the sine of an angle. Now, again, sometimes you're going to be given questions that are using values that are already on your unit circle. Sometimes you'll just have to do the arithmetic. So for instance, let's say I had a problem like the sine of an angle is square root of 3 over 2, and I ask you to find cosine theta. Now typically in problems like this, you're going to be told that your angle is in a certain quadrant. That's because if I look at my unit circle, and again, we just defined sine of theta as being square root of 3 over 2, I have two values that have that same sign. I have 60 degrees, which has a sine of radical 3 over 2, and 120 degrees, which has a sine value of square root of 3 over 2. So because of that, typically a question on a standardized test will tell you, find cosine if theta is in quadrant 1 or theta is in quadrant 2, etc. Okay, so let's say I specified for number 1 here that my theta is in quadrant 1. Then if it is a value that's on the unit circle, I don't have to do any arithmetic. I can just go to where I have radical 3 over 2 for sine, and then look at the cosine value, which is x. So cosine theta is 1/2. Now, if I didn't have a unit circle handy, or if it wasn't a value on the unit circle, and again, we can do a number of things, but let's say I say sine of theta is 0.6, right? That, of course, is not going to be on my unit circle. Again, I'll specify which quadrant it's supposed to be in. Let's say theta is in quadrant 1 again, okay? So if I don't have it on my unit circle, that means one way that I can solve for this is by using the Pythagorean identity. So here, I would substitute sine of theta for 0.6. So sine of theta is 0.6 squared equal to 1. And I would solve this just like any other algebra problem. Now, a lot of students get confused when they see either sine squared theta or cosine squared theta written. This is just like writing the sine of an angle squared, but it's saving us from having to write parentheses. Similarly, cosine squared theta is cosine theta quantity squared. So if that's confusing you, you could substitute in x or y if that helps you as you're doing the algebra steps. But basically, we're getting the variable term by itself and then getting the variable by itself, just like any other two-step equation. So first here, I'm going to do 0.6 squared, which gives me 0.36. I'm going to subtract 0.36 from both sides to give me 0.64. And then I'll take the square root on both sides, which gives me cosine theta equal to plus or minus 0.8. Again, there's always going to be two values that have the same sign. So there is one angle that has a sign of 0.6 that's going to be in quadrant 1, and there's one sign value that's going to have a value in quadrant 2. So to determine which of these it is, positive or negative, you have to think in terms of the quadrants. Quadrant 1, and you can put this in your notes if you don't have it already, but remember that in quadrant 1, both x and y are positive. In quadrant 2, x is negative, y is positive. In quadrant 3, x and y are both negative. And in quadrant 4, x is positive, y is negative. So if I'm told from my given information that my angle is in quadrant 1, that means my cosine value has to be the positive 0.8. Okay. Now, one of the questions in your notes is going to ask you, do you have to use a Pythagorean identity? Well, no, you don't have to. We could write out a sample triangle. It doesn't have to be to scale, right? And if I define sine of theta as being 0.6, well, I could write this, for instance, as a fraction. That's 6 over 10. So by converting the decimal to a fraction, then I can use my ratios. I know sine is opposite over hypotenuse. And so if I can solve for the adjacent side, then I can write cosine, which is adjacent over hypotenuse. This would then be a Pythagorean theorem problem instead of a Pythagorean identity problem. So here, this would be 6 squared plus x squared equal to 10 squared. 6 squared is 36. 10 squared is 100. I would subtract 36 on both sides, and then I would take the square root. By defining x as plus or minus 8, that would mean cosine is plus or minus 8 over 10. And I would still need to identify which quadrant it's in, but 0.8 is the same as 8 over 10. So you can always fall back to your Pythagorean theorem if you need to, but the idea here is that you're using the Pythagorean identity. That's the goal. Okay. Let's do another example. Again, looking at decimals, let's say a sine of my angle is negative 1.23, or sorry, negative 0.123 rather. And I want to find cosine. And let's say in this case that the angle is in quadrant 3, for instance. So same thing. The goal is that you are using your Pythagorean identity. So that would be sine squared theta plus cosine squared theta equal to 1. Plug in your negative 0.123 squared plus cosine squared theta equals 1. You would be doing 0.123 quantity squared, which, pull up a calculator here. So we can do 0.123 squared, which gives me 0.015129. You can round, but typically if you're doing something like this, you want to round as your last step so that your final answer is not way off. Okay. Okay. Then I'm going to subtract the 0.05129 from 1. To give me 0.984871. And then I'm going to take the square root on both sides. Oops. To give me 0.99, and I'm going to round to the nearest thousandth, 0.992. Of course, this is plus or minus. Now, because I specified that my theta is in quadrant 3, that means I'm looking at the negative value here, so negative 0.992 would be my answer. Even if it's a larger decimal, I could still write sine of theta 0.123. I could still write that as a fraction. This is, 3 decimal places, so that would be negative 123 over 1,000. But then I'm looking at an angle or a ratio where I have to do multiples of 1,000. It ends up being honestly the same amount of work, but whichever one you're more comfortable with, you're going to end up with the correct answer. That's it for today, guys. If you have any questions, please reach out to me. Otherwise, have a good day, and I will talk to you soon. Bye.